Welcome to a deep dive into proteins, those tiny powerhouses that make life tick. We're talking muscles, disease fighters, even the microscopic machines driving your metabolism.
Right, proteins are like the ultimate multitaskers. And their most mind-blowing trick, it's all about how they fold.
Exactly. It's origami, but on a microscopic level. So we've got these chains of amino acids, and somehow they fold into these crazy, intricate 3D shapes. And it's those shapes that determine what each protein actually does.
Yeah, for ages, scientists were stumped trying to predict a protein's 3D shape just from its amino acid sequence. But guess what? The 2024 Nobel Prize in Chemistry went to 3 scientists who cracked that code. We've got the official Nobel documents and some easier-to-digest stuff to guide us, so get ready.
Okay, hit me with it. Who are these science superstars?
The Nobel went to David Baker, Demis Hassabis, and John Jumper. Each one tackled this problem in their own unique way.
Oh, I love a little scientific rivalry. So where do we kick things off? Give me a story.
Let's start with David Baker. Picture this. He's like a master architect, but instead of buildings, he's designing proteins.
Okay, I'm intrigued.
Baker started by studying how proteins fold in nature. But then, he took a giant leap and created this revolutionary software called Rosetta.
Rosetta. Okay, I'm getting serious. Rosetta Stone, unlocking ancient secrets. Vibes here. Does this software, decipher the language of proteins?
You're closer than you think. Rosetta allows scientists to do something once thought impossible. Design completely new proteins from scratch. We're talking proteins with structures never found in nature. They call it de novo protein design from the beginning.
Hold on, back up. From scratch. As in, they can just dream up a protein and build it? Where do you even begin with that?
Well, in 2003, Baker's team did exactly that. They designed a protein called Top7, completely unlike anything found in nature, and it folded exactly as Rosetta predicted.
Wow, so they proved it could actually be done. That's huge. What else has Baker's team created with this Rosetta software?
They've designed proteins that assemble themselves into tiny cages. Imagine them as microscopic delivery systems. And get this, they've created molecular switches, proteins that can be turned on and off, which could have tons of uses in biotechnology. They even designed a protein that can bind to fentanyl.
Wait, fentanyl as in that incredibly dangerous opioid?
That's the one. This protein they designed could lead to new ways to detect it, maybe even save lives.
Wow, from tiny cages to taking on the opioid crisis. That's a pretty big impact. Okay, so we've got Baker, the protein architect. Now, tell me more about Demis Hassabis and John Jumper, the AI masters. What did they bring to the party?
These two are the brains behind AlphaFold, and here's where things get really wild. Imagine a computer program that can predict a protein's folded shape just as accurately as years of lab work. That's AlphaFold.
Hang on a sec. Are you saying AI can now do what used to take scientists forever? I'm going to need the layman's explanation on this one.
It's all thanks to deep learning. Hassabis, who's got this super interesting background in chess and neuroscience, was already making waves with AI at Google DeepMind. He teamed up with Jumper, a theoretical physicist, and they decided to tackle this protein folding puzzle head-on. Basically, they fed AlphaFold a massive amount of data, like a giant protein encyclopedia.
So they basically force-fed this AI all the protein knowledge they could find, hoping it would figure out the patterns. Pretty smart. What happened next? So last time we dove into the world of protein design and how scientists like David Baker are using software to build totally new proteins right from scratch.
Yeah, like building them brick by brick.
Exactly.
Right.
But before we got lost in the protein design world, we were talking about AlphaFold, this AI created by Demis Hassabis and John Jumper that can predict protein structures. I'm dying to know more what happened after they unleashed this data monster on the protein world.
Well, in 2020, they came out with AlphaFold 2, an even more powerful version.
AlphaFold 2, okay, so like an upgrade.
Exactly. Picture this. You give a computer a giant jigsaw puzzle of all these different protein shapes, and you show it millions of protein recipes, and it figures out how to put that puzzle together.
Wow, that's a seriously cool visual. So basically, AlphaFold 2 learned how to connect the dots between amino acid sequences and the 3D shapes they make. Did it actually work, though? Could it really predict those structures accurately?
It wasn't just accurate, it blew everyone away. There's this big protein prediction competition called CASP. And AlphaFold 2 just aced it, scored higher than anything else ever.
No way. So this wasn't just some cool idea. It was a total game changer. We're talking about an AI that's as good as, maybe even better than, years of super careful lab work. What does that kind of accuracy even mean for science, though? Why should we care?
Okay, so think about diseases like Alzheimer's or Parkinson's. They're linked to proteins that are folded the wrong way, misfolded.
Folded proteins, got it.
And with AlphaFold 2, we can now predict those misfolded structures really precisely.
So it's like having this detailed map of what's going wrong right down at the molecular level. That could be huge for developing new treatment.
Exactly. We could target the root of the problem, those misfolded proteins, instead of just dealing with the symptoms.
That is incredible. It's like we're finally figuring out how to speak the language of disease. What about drug discovery, though? I bet having this kind of protein predicting power is a game changer there, too, right?
You got it. Drug development can take forever, and it often involves a ton of trial and error. But AlphaFold 2 lets scientists test out millions of potential drugs virtually and see how they interact with a target protein before they even step foot in the lab.
It's like having a superpower that lets you see if a drug will work before you even try it. That's insane.
It's all about working smarter.
Yeah.
Imagine how much faster we could come up with new antibiotics, antiviral therapies, even personalized medicine designed just for you based on your own proteins. The possibilities are endless.
Okay, so we've got the medical world freaking out, but what about the bigger picture? Things like the environment, climate change, sustainability. Does this protein revolution have any impact there?
Oh, absolutely. Imagine designing enzymes that can break down plastic, which normally takes centuries to decompose, or engineering tougher crops that can handle drought and disease, which is super important with climate change.
It's mind-blowing to think that by understanding these tiny proteins, we could tackle some of the biggest challenges we face. It feels like the future of science has officially arrived. So we've got David Baker building proteins from scratch, and Demis Hassabis and John Jumper predicting how they'll fold with AI. What's next?
It's a really incredible time to be alive, wouldn't you say?
Yeah.
And it just goes to show the power of collaboration. You've got computer scientists working with biologists and chemists, all on the same team. And that's what makes these breakthroughs so exciting.
It really is the ultimate meeting of the minds. So we've talked about the what and the how of this protein revolution, but the big question is, what does it all mean? What does the future hold? Join us for the final part of this deep dive, where we'll be exploring just the good, the challenging, and everything in between.
Welcome back for the grand finale of our deep dive into the protein world. We've gone from building new proteins with software like Rosetta.
Like crafting them with molecular tools?
Yeah, it's pretty wild. And others predicting their shapes using AI like AlphaFold.
It's been an amazing journey, hasn't it? From the micro world to the future of, well, everything.
Totally. Before we unleash our listeners to ponder all the possibilities of this protein-powered future, I want to know, where do you think we go from here?
The big question. It's like we've stumbled upon the scientific goldmine, right? We can design proteins, predict how they fold, even manipulate them at the atomic level. It's mind-blowing.
It's like we suddenly have superpowers, but we're still figuring out what they are. Exactly. Imagine a world where plastic waste is a thing of the past because we've designed enzymes that can break it down super fast.
Now that would be a game changer. And it's not just the planet, right? What about the possibilities in medicine?
Oh, the potential is incredible. Personalized medicine tailored to your unique proteins could be the norm. We could see diseases like Alzheimer's or Parkinson's diagnosed and treated way earlier, maybe even before they really start.
It's like sci-fi coming to life.
Yeah.
But here's the thing. With great power comes great responsibility, you know? We're talking about having the tools to basically redesign life itself.
That's a really important point. We're venturing into uncharted territory here, and we need to be incredibly thoughtful about every step we take. Ethics have to be front and center with every new discovery and how we use it.
It's a good reminder that science might be pushing the boundaries, but we have to make sure we're using this knowledge for good.
100%. The future of protein science isn't something that just happens. It's something we create together. Scientists, ethicists, policymakers, everyone. It's a future full of potential, but it's our job to make sure we use it wisely.
Well said. To everyone listening, we hope this deep dive has left you feeling inspired by the incredible world of proteins and what we can achieve through science.
It's been awesome joining you on this adventure.
And remember, the future isn't set in stone. It's something we build together. One question, one discovery, one protein at a time. Thanks for diving in with us, and until next time, stay curious.